Today I'll be talking about the optimal time-space trade-off for hashing tables. And this is joint work with Michael Bender and Martin Froch-Colton, who are in the audience. So sorry, Martin, that I didn't include your full name. And also with Bill Kuszmaul and Mingmao Liu. OK, so what is a hash table? So a hash table is any data structure that solves the unordered dictionary problem. So what a hash table has to do is it has to maintain a set S, which is a subset of some universe U. And it has to be able to handle the three operations: insertions, where we add a new element to the set S from the universe; a deletion, where we remove an element from our set S; or a membership query, where you ask, is X in your set S? And you have to say yes or no. So we require that membership queries for hash tables take constant time deterministically. And insertion and deletion times will occasionally take expected constant time, but for all of our upper bounds, they'll be with high probability constant. OK, so the size of our set S is n. And this is actually the size of S at time, at a given time. So it's not an upper bound. It's not the maximum. It's actually the size of S at a given time t. And generally, we're going to say that the size of our universe is such that our word size W is equal to the log of the universe. And this is at least log n. OK, so this is what a hash table does. It does these three operations.
So I didn't understand your comment about n. So n is, do I think of n as a changing parameter?
Yeah, so n is a parameter that changes over time. So your hash table might be small, and then it might.
But you're right, the word size. The word size presumably is not changing. Oh, it's greater than log. So it's greater than log the maximum of n?
Yeah, that's right. Thanks for pointing that out. But yeah, so n is growing and shrinking over time. And so for space efficiency, we mean if you're space efficient in n, you're space efficient in the number of items that are currently in your hash table, not the maximum, but the current number. OK, so speaking of space efficiency, what's the right way to think about a space efficiency for a hash table? So if you're storing n keys from a universe of size 2 to the w, where w is your word length, then we can express space usage as the sum of two components. So first, you have your information theoretical lower bound. So this is log of 2 to the w, choose n. And then additionally, you have the other bits that your hash table uses, r times n. And so here it makes sense to think of r as sort of the number of bits that you're wasting per key, the number of bits per key that you're going beyond the information theoretical lower bound. And so the big question, the central question for this talk is, what is r? How many bits do we actually have to waste per key? OK, so what's the history of upper bounds for r, for the number of wasted bits per key? So in traditional hash tables, the value of r is big omega of log u. So just, for example, if you just have a hash table that's using linear probing with a constant load factor, for example, it's like if half of your table is empty, then you're wasting log u bits per key. In 2003, a bound of big O of log u was proved with expected constant time insertions and deletions. So this is decreasing the number of wasted bits by from log u to log u. And subsequent work improved this insertion deletion time from constant expected to high probability expected. So for each of these papers, they all prove high probability bounds for more and more succinct hash tables until the final one is actually for log u with high probability constant time insertions and deletions. OK, so this is the state of the art, is big O of log u. And the question is this actually the optimal value of r, log u? And there's a lot of reasons to think that it probably is. It might well be. Because for many related problems, we do have established lower bounds of omega of log u wasted bits per item. So for example, for the dynamic retrieval problem, So this is a similar problem, but instead of storing only keys, you're storing key value pairs, and you only receive positive queries. You never receive negative queries. For that, we have a lower bound of big omega of log log u. For dynamically resizable filters, we also have a lower bound of big O of log log u. And this is true even for, this is true for all dynamically resizable filters, even just the very simple case where you have a filter that you're incrementally inserting items into it, and it's growing over time. And we also have the same lower bound for stable hashing. So this is the unordered dictionary problem where wherever you first store a key, you're not allowed to move it later. You have to continue to store it at that location until you delete the key. So the central question is, does this lower bound of big O of log log u, wasted bits per item, does this apply to hash tables? And the answer is no. And in fact, it turns out we can actually establish a much, much tighter upper bound. So our result is that for any k at least 1, any k greater than 1, we can achieve a big O of k time insertion and deletion with high probability. So our hash table has operations of insertions and deletions that are big O of k time with high probability. And the number of wasted bits per key is r only big O of the kth log of u.
Kth iterated log.
Kth iterated log, yeah, thank you. So, for example, you can get constant time insertions and deletions with the big O of 1th iterated log of u. So if k is constant, you get the kth iterated log wasted bits per key for free with constant time insertions and deletions. And if you're willing to spend log star of n time doing your insertions and deletions, then your number of wasted bits is constant per item. OK, so the question is, now that we have this upper bound, is this the right answer? Is big O of the kth iterated log of u the right answer for the number of wasted bits in hash tables? And the answer is sort of maybe. So it turns out we can establish a lower bound for a large class of hash tables that encompasses all succinct hash tables. And to see what this class is, let's first define what this class is. And let's start by looking at open addressing hash tables. So in an open addressing hash table, every element x in our universe has a sequence of hash values, h1, h2, so on and so forth. And you have a storage array. And each of these hash values maps to an index in the storage array. So for example, h1 of x, your first hash value maps to that location. And h2 of x and h3 of x map to different locations in the storage array. And for x, maybe we end up placing it in this index, so it's actually mapped to by its third hash value. So this is open addressing, and this is a very classic way to do hash tables. This is how linear probing works. This is how cuckoo hashing works, quadratic probing, uniform probing. And recently, however, all succinct hash tables have used not only open addressing, but augmented open addressing. So the way augmented open addressing works is you continue to have every element have these sequence of hash values, but you also have a query router, where every element that's in the table is placed in this query router, and it's mapped to the index in its series of hash values. So here, x is mapped to 3 because it's stored in h3 of x. So now when a membership query for x is received, you look up x in your query router, you find 3, and then you go to h3 of x in your storage array to find that x is there. And so this is why membership queries are deterministically constant time. And so this is all known succinct hashing schemes use augmented open addressing. They all have storage arrays of 1 plus little o of 1 times n. And they all have constant time query routers. Okay, so the theorem we prove, the lower bound we prove, is that any augmented open address hash table that moves big O of k items per insertion and deletion has a query router of size at least big omega of n times the kth iterated log of n bits.
So, sorry, where did the space needed to store the hash functions themselves? But where did the hash functions themselves come from? Are they?
In the upper bound?
Well, either. I mean, I guess.
In the lower bound, we're just bounding the size of the query router, so it doesn't matter how much space it takes to store the hash function.
I see.
The query router is already this big. And in the upper bound, we have something that matches this and stores an explicit
Okay,
hash
so
function.
in the lower bound, you're giving me, I mean, you're giving me this extra freedom to pick whatever hash functions I want.
That's right.
And I don't pay for that at all.
Yeah, any series of hash values you want. Oh, okay, so that answers the question.
Yeah.
Okay, so this is our lower bound, is that our query router has size at least n times the kth iterated log of n bits. Okay, and so since our query router has size at least n times the kth iterated log of n, that means if you're using an augmented open addressing hash table, then you're wasting at least the kth iterated log of n bits per key. Okay, so what are the consequences of this lower bound? So to beat this bound, we need a really new approach to constant time hash tables, something totally outside the scope of augmented open addressing. And so I think this is a sort of a very significant open problem is, can we extend this lower bound to cover all hash tables? Our upper bound is tight for this class because we match this bound of kth iterated log of n wasted bits per key. So one of the reasons for this is because our storage array is actually exactly n slots rather than 1 plus little o of 1 times n slots. And this means that all of our wasted space is in the query router, and we use a query router that's optimal. So let me give a little bit of intuition for sort of the flavor of our lower bound. And just to tell you that sort of the way we think about sort of achieving this lower bound is by considering something called the probe complexity problem. So for an element x in our hash table, if we store x in hi of x in our storage array, then we're going to say that the probe complexity of x is 1 plus log I. So you're storing it in hi of x and its ith location and its series of hash values, and its storage complexity its probe complexity is 1 plus log I. And it turns out that it's possible to implement a constant time query router that uses only big O of the probe complexity of x bits per key x. And sort of the conclusion is that from the perspective of an upper bound, we should be minimizing the average probe complexity. And so this is how we establish the upper bound, is by showing that it's possible to minimize this probe complexity. And for the lower bound, we say that this trade-off curve is asymptotically tight. And the proof sort of considers, well, how much can you really gain? How much can you reduce the probe complexities by swapping items? And so it uses a fairly involved potential function argument. Thank you.
So how complicated is it to describe the family of hash functions you use in the upper bound?
It's.
I mean, is it a 1-minute answer? Is it a 15-minute answer? That's what
It's not that simple an answer. It's a little involved.
We didn't do anything new, we just had to bolt together a bunch of existing results on explicit hash function constructs.
Yeah.
The idea for the potential function is that short, you have these augmenting paths of I'm going to move this, and then that's going to move that, and so on. You have these chains. And there just aren't very many short augmenting paths. There are a lot more long augmenting paths. And so you just don't get that much from using these short augmenting paths. And so if you have, if you don't move very many balls, that's equivalent to shooting using these short augmenting paths and getting very little benefit, so that you don't improve the average probe complexity by that much. And it's 30 pages later. It's ta-da! So it's a little messy.
Yeah. So every extra move swap you allow yourself to do gives you an extra log in your iterated log, basically.
Other
Is
questions?
Is there hope to get like R smaller than 1 redundancy with non-trivial worst case update time?
Smaller than 1.
Redundancy, like R and redundancy with R smaller than 1.
With constant time queries?
No, with non-trivial worst case query.
Like,
Constant, I guess that would be the best. But any non-trivial is that?
so allowing the query sizes to be probabilistically constant, for example, or?
Yeah, like constant query, or maybe constant time. Sorry, query time matches the update time, but not trivial.
If R is less than 1, then you have to have a perfect hashing scheme, and so your array has to be exactly of size.
And also, I think you probably need encoding better than just storing the elements, because storing elements already waste constant bits.
I think for perfect hashing, you need log E wasted bits
Yeah.
per item, but I don't know whether that assumes something about the queries. I don't remember if that assumes something about the queries. As soon as you allow yourself more or less any reasonable number of spare slots in your array, and there are universes that will make that a bigger term than your routing filter, and so you really have to actually have exactly n slots. And so I believe log E is the lower bound in that case.
Okay.
So you mentioned a bunch of hashing schemes that use open addressing, but are there also like natural ones that don't use it that could potentially break the lower bound?
Certainly not that I know of.
They're not succinct.
Because, yeah, I mean, virtually nothing, none of the traditional hash tables are actually succinct. Is one issue.
So do you think that the lower bound should hold in general?
Yeah, I do.
So is there a natural, like if you look at your lower bound and what it needs, does it suggest like a natural augmentation of the model that your lower bound will not handle? That's what, so the question is like, can you enlarge your model in some natural way to give yourself an interesting question?
Give your machine a little more horsepower somehow.
That's right. That makes it harder for your lower, that breaks your lower bound. Do you know any? And that would be like the next intermediate step to proving, the impossibility.
That's a great question.
Yeah, that's a really good question.
Okay, you can tell me the word.
Huh?
You can tell me the word.
I can't think of anything off the top of my head.
All right.
Thank
Any other questions? Thank you.